All right. So yeah, chapter 9. And we're going to be talking about the repeated measures t-test. I want to review a little bit on the one sample t-test, which is what we've talked about last time. Here is the formula for the one sample t-test. And so I guess a good place to start is remembering. So here's the t statistic that we calculated. There's one essential difference between this and the z statistic that we computed in chapter, let's see, when was that? Chapter 7. That's when we did a lot of computing of z statistic. What is the primary difference between the t statistic and the z statistic as far as the equation? Can anyone remember this?
For the t statistic, the standard deviation for the population is unknown. But also, I don't think you're sharing your screen.
Oh, good, thank you. Yes, that is important to know. Okay. Now you can see my screen. And yeah, so here is the t formula right here. So, and yes, that was mentioned that for the t formula, the population standard deviation is not known. So what do you use instead in the t formula? Since the population standard deviation is not known, what do you use instead in the t formula?
The sample standard deviation.
The sample standard deviation, which is this symbol right here, which is S. So really, it's exactly the same as the Z formula that we used. M is sample mean, mu is a population mean. We still have a standard deviation here, but now it's the sample standard deviation because we don't know the population standard deviation. We still have the square root of the sample size in the denominator. And just focusing in on the sample standard deviation, here's the formula for sample standard deviation. And notice how for this formula, it's got the n minus 1 in the denominator. The population standard deviation equation has just n in the denominator, but the sample standard deviation has n minus 1 in the denominator. And I'll point out, to avoid confusion, that whereas the sample standard deviation has n minus 1 in the denominator here in this part of the t equation is still just a straight up n. There's no minus 1 here. So it's not like everything is n minus 1 in the denominator for the t statistic. S has n minus 1 in the denominator. The sample standard deviation does. But t still has a regular old n in the denominator. So that's the one sample t-test. Maybe we should talk a tiny bit about the situation in which you use one. So here's an example that I gave you. I worked out the math for you as well. Here's an example I was completely made up. I think I said this was 10 questions on a true or false test. And the mu for a one sample t-test like this is often hypothetical population mean or chance performance. Mu for the one sample t-test is oftentimes inferred or derived from using probability theory. And I mentioned for this example last time that our mu for this example was 5. Could someone remind me, how did we derive 5? How did we infer 5? Remember, how did we get that number 5? The sample mean is 6. So where is this 5 coming from? Anyone remember, how is that inferred or derived?
It's a hypothetical mean.
Yep. And what was the basic calculation that was used to infer it, to get at that number 5? Like, where does that 5 come from mathematically? Or like, what was the simple mathematical calculation that was used to derive it?
I don't remember. Sorry.
No, it's okay. Anyone. If she's right, it was definitely, it's a hypothetical mean. How did we get that number 5? I'll remind you, there was, on each person, it was a 10 question quiz or test, and all of the questions were multiple choice. How many answers on average, if a person was guessing on a 10-question multiple choice test and they guessed every single question, how many questions would you expect them to get correct?
I think last time you were saying they were true false questions, so it'd be 50 out of 50.
Yeah, did I say not true false? Did I say multiple choice?
Yeah, you said multiple choice, but I mean, same thing.
Yeah, I meant to say for sure true false. I'm sorry, I confused you there. Yes, true false. It is true false. There's two possible answers on each question. So 10 true false questions, and you have a 50% chance, therefore, of getting each question on the test correct. So this number 5 right here is derived because you're taking the total amount of questions on each test, 10, and dividing it by 2, or similarly multiplying it times 50%. The odds of guessing correctly is 50%, and there's 10 questions. 10 times 50% equals a score of 5. 5 is how many questions you would expect to get right if you were guessing on every single question. The people actually got 6 answers correct on average. If you add up these 5 scores and divide by 5, you would get the sample mean was 6. What this one sample t-test is comparing is whether this one sample right here, which is 6, is significantly different than chance performance if people were guessing on every question, which would be 5. And it's telling you, are these two numbers, 6 and 5, are they significantly different from each other? And we got this t value. Okay, so now we're moving on to the repeated measures t-test. So the one sample t-test is actually kind of weird for various reasons, and the reason it's weird is because there's only one sample in it. And I guess I should point out that one sample in the one samples t-test is this M right here. We have that one sample that we calculate a mean for, and is the M, and we're comparing it to a hypothetical population mean. But it turns out that in actual psychology experiments, usually what you do as a researcher is you have 2 different conditions, and you compare the means of those 2 different conditions. That's actually what is done with the repeated measures t-test. So let's kind of look at what's going on here with the repeated measures t-test. I guess this would technically be our 3rd hypothesis test that we have learned to perform. We've done just the one sample z test, the one sample t test, and now we are doing the repeated measures t test. So this is the 3rd hypothesis test that we're going to learn. I, in my head, actually call this the within subjects t test. But they're basically synonyms. Repeated measures t-test or within subjects t-test. It is also sometimes called paired t-test. There's multiple names for this t-test. But the really crucial thing about within the repeated measures t-test is that we have a within subjects factor. And so a within subjects factor, which we have talked about what this means, a within subjects factor is when for each condition of the independent variable, each participant contributes a score. It says it right here, 1 score for each condition. And so if we have 2 conditions of our experiment, condition 1 and condition 2, then me as a participant, I give a score for condition 1, and I also give a score for condition 2. And that's the way it is for all of the participants. They contribute a score for condition 1, and they contribute a score for condition 2. And then what the repeated measures t-test is doing is it's comparing those scores across all the participants, is comparing those scores between conditions 1 and 2 to see if the mean of condition 1 is different than the mean of condition 2. All right, so here's the formulas that we're going to be dealing with. It's for the repeated measures t-tests. So here's the formula right here that we're going to be dealing with in this for the remainder of this chapter for the repeated measures t-test. And I'll point out that this is the one sample t-test that we were just talking about. So in the repeated measures t-test, it's structurally identical. I say structurally similar here, but really it's structurally it's identical as the one sample t-test. The one sample t-test looks like this. The repeated measures t looks like this. Structurally, they're the same. The only difference, and you can kind of see it visually, is there's D's next to each one of these letters right here. M sub D, mu sub D, S sub D, N sub D. That's the only difference. And so we're going to have to understand what those D's mean. I'll tell you now. Those D's stand for difference scores. That is what the D stands for. And that's what's stated here. Based on difference scores, D's rather than X. So when we're calculating this, we're just typing in, raw scores. That's what's used for this. Here, we're using things known as difference scores. And so I'm going to have to show you what difference scores are. And then we're going to be calculating the t-statistic using difference scores instead of using just X values and means of X values like we did over here. So a difference score, D, equals, for a given participant, as I said, if we're just doing this, the simplest example would be there's two conditions. There's condition 1 and there's condition 2. I contribute a score to condition 1. I can just contribute a score to condition 2, and every participant contributes a score to each of those two conditions. The difference score is taking my score in condition 1 minus condition 2, or vice versa, taking my score from condition 2 minus condition 1. So here I'm showing both ways. D equals my score in condition 2, right here, X2 minus X1, or similarly, my score in X1 minus X2. So it actually does not matter which order you do these things, as long as you do it the same order for every participant in the t-test. So it doesn't matter which way you do these differences. You just have to do it consistently for all of the participants in your study, and it will work out just fine. So it doesn't, either both of these are right, just be consistent. Either use this one or this one, and you'll be fine. So we will be dealing with these difference scores in a second. We will also be dealing with something called a sample mean difference score. So the sample mean difference score, or M sub D, is for all of the participants. Each participant contributes the score for those two conditions, condition 1 and condition 2. And you get it. And you get a D for each participant. The mean of the difference scores, M sub D, is basically adding up all of those difference scores for all of the participants and then dividing by the number of participants there are. So I will give you examples of how to do both of these, I think, coming up very soon. Yeah, right here. This does both. So here, let's move this darn thing. Okay, so here is an example of some data. A, B, C, and D, those are the people, those are the participants in our study. Condition Roman numeral 1 is condition 1, Roman numeral 2 is condition 2, D is the difference. Each of these things right here is that participant's score. This is the scores of the 4 participants for condition 1. This is the score of the 4 participants for condition 2. Please notice that subject A, person A, whoever that is, they gave us a score for condition 1, but that participant also gave us a score for condition 2. This is what within subjects means, that for each participant, they give scores for all of the different conditions in the study. And so now we want to look at the difference scores, because that was one of the first things that I said all of this repeated measures t-test is based on the difference score. So they got this number 4 here by taking X2 minus X1 equals 4. X2 minus X1 equals -2. X2 minus X1 equals 3. X2 minus X1 equals 1. So those are the D's. Those are the difference scores. That's pretty straightforward, I believe. So clearly in this case, they were taking the scores of X2 minus X1, but as I mentioned, you can get the final result of calculating this T will not be functionally different if we would have done it in reverse. 1 minus 2, 1 minus 2, 1 minus 2, 1 minus 2. that would give us the same end result as what we just did right here, which is 2 minus 1. As long as you're consistent with how you subtract to get the D's, you'll be good. So those are the different D's for this sample size, by the way, of 4. And so how do we calculate M sub D? That is showed right here. Remember, M sub D is the mean of those different scores. And so all you do is you add up those 4 scores, 4 plus minus 2 plus 3 plus 1. That equals, let's see, 2, 5, 6, divided by the total amount of different scores, which is 4. 6 divided by 4 equals 1.5. So our mean difference score right here is 1.5. Any questions or comments so far about how I've calculated those D's and how we calculated the mean of the different scores? All right, let us move on. Okay, so here is the formulas that we're going to be using again. Here is the t-test for the repeated measures t. Please keep in mind, once again, the only difference between this one and the one sample t-test is this one has all these D's in it. Oh, and I could have put a D right here next to the N. I forgot to put the D right there. But the repeated measures t-test, all of these things have D's next to them, which means that these numbers are based on different scores instead of raw X values. We already know how to calculate this right here. We will also deal with calculating these things over here in just a few minutes. So a couple more things. This thing right here, it's got 2 subscripts. This is the sample mean. This is the estimated standard error of the different scores. The estimated standard error of the different scores. With the one sample t-test, we had estimated standard error, which was sample standard deviation divided by the square root of n. Here we have the same thing, estimated standard error, but it's estimated standard error for the different scores. So that's why this D is here, different score, estimated standard error of the different score. And all this is the standard deviation, the sample standard deviation of the different scores divided by the square root of n. So how do we calculate this? The sample standard deviation of the different scores. Our formula for that is right here. Here's the sample standard deviation of the different scores. What we do is we take each different score and subtract from it the mean difference score. You square that, add all of those things together, divide by n minus 1, and then take the square root of that. And that's how we get the sample standard deviation of the different scores. So really, this is the same old sample standard deviation equation that we were using for the one sample t-test. The big difference is now we have a D here instead of X. And now we have M sub D here instead of just an M. So it's really not that structurally, it's the same as any old sample standard deviation equation. The main difference is that we have the D's in there. So it'll help to do some actual examples. We'll get to the examples in a second. I just want to show you a couple of these things right here. We'll be dealing just briefly with these things right here. So the degrees of freedom, once we eventually get to our T table, and we want to look up the critical T value for, to determine whether the T that we're going to calculate is be in the critical region or not. The degrees of freedom that we're going to use for the repeated measures t-test is exact same as the degrees of freedom we would use for a one sample t-test. That is just the sample size minus 1. So degrees of freedom hasn't changed for us. It will change when we start doing independent measures t-test in the near future. But for now, degrees of freedom is just n minus 1. Our null hypothesis is mu sub d equals 0. So we need to think about what this means. We have these 2 conditions. In the null hypothesis, what that means is there's no difference in the scores among those 2 conditions. That's what the null hypothesis says. There's no difference among the conditions. And so if we have a study with 2 conditions and the null hypothesis says there's no difference among those 2 conditions, then when you calculate the difference score, you would expect the difference on average to be 0. which is what this is. Mu sub d equals 0 basically is saying when there's no effect, when there's no difference between in the means of the two conditions, then when we're calculating the difference score, the score of x, the score of condition 2 minus the score of condition 1, when we do that for all of the participants and then take the mean of all of those different scores, that mean should be 0. If there's no difference between the two conditions and we take those different scores for all the people, add them together, divide by the total amount of people, that mean should be 0. So this is the null hypothesis. The mean difference score should be 0 is what this says. The research hypothesis just says, we should be used to this kind of idea by now, that the difference score is not 0, which means that the mean difference score could be greater than 0 or the mean difference score can be less than 0. This is the research hypothesis right here. Okay. So let's just get a little bit of practice calculating difference scores right here. So to make sure that I'm going to kind of do these, but you might want to start doing these. This is an example of, this is another example. This is an example we can calculate a repeated measures t for, and I will calculate the repeated measures t for this example right here. So what we have is an example where it's babies are looking once again at attractive and unattractive faces. I've changed it a little bit since the example earlier on in the chapter, where now I'm making it where the babies are only looking in total for 10 seconds. Last time I made it where the babies were looking in total for 20 seconds. Now the babies are looking in total for 10 seconds. We can tell, by the way, because 5 plus 5 equals 10, 7 plus 3 equals 10, 6 plus 4 equals 10, 6 plus 4, all of these 6 plus 4s, all equals 10. So in each chapter, there's two faces, or in each trial, there's two faces on the screen. One of them is attractive, one of them unattractive. The baby looks at the computer screen for 10 total seconds. They're either looking at any given point in time at the attractive or unattractive face. We're counting the amount of time that the baby spends looking at each type of face, attractive versus unattractive. There are 10 total seconds in the trial. So when we add up the total amount of time looking at each face, it should always equal 10. And so what we're going to be using the repeated measures t-test to do here is to compare, is the mean amount of looking time looking at the attractive face, is it different than the mean amount of time looking at the unattractive face? Are the mean amount of time looking at each of these two conditions different? So in order to calculate repeated measures t, we have to calculate those difference scores. And so I like to avoid negative numbers whenever possible. And so I noticed the best way to do that would be to take this d minus this d, and then we'll do that for all 10. So you might want to start kind of doing that in your head or maybe on a piece of paper. I'm about to start doing it right now to make sure you can do it. So I'll have to get out of here. Oops. All right, I think I can type these in here. So 5 minus 5 equals 0. 7 minus 3 equals 4. 6 minus 4 equals 2. 2, 2, 2, 2, 2, 2, and 2. So anyone have any questions as to how I got these different scores? I know I did a lot of them real quick. Of course, a lot of them were that same thing, 6 minus 4 over and over and over again. I think I did these right. Any questions or comments about how I got these Ds? These are the different scores. All right, let's move on. All right. Okay, so here's the same data. This is shown at the top of this slide this is a screenshot from Microsoft Excel where I have calculated using the repeated measures t formula. I've calculated repeated measures t, and we're going to kind of break this down into the different components to work out how to calculate t for this exact example right here. Repeated measures t. Let's see. So let's actually go back to our formula real quick. So we need to get this m sub d and we need to get the standard deviation right here. We already know what this number is going to be. Mu sub d in every repeated measures t-test will always be 0. This is because of the null hypothesis, and I want to show you that real quick. The null hypothesis says mu sub d equals 0. Therefore, mu sub d is always 0, which is kind of helpful for you. Basically, that means you can always ignore this part of the repeated measures t because it's always 0. All you really have to care about is this m sub d, which we're going to calculate, and then the denominator, which is the standard deviation of the different scores divided by the square root of n. So you can kind of ignore this part of the equation, and all you really have to worry about is this stuff over here. So let's do that. The two things we really care about right now are calculating m sub d and s sub d. I think we can probably already tell quite easily what n is going to be. What is n going to be? Can someone tell me what is n going to be? I'll give you a clue. It has to do with these things right here.
10.
It is 10. There's 10 people. Okay, so m sub d is calculated right here. And you notice here the d's, I've labeled this with d right here. And these are the exact same numbers that I typed in on the previous slide, except they're already done for us. 5 minus 5 equals 0. 7 minus 3 equals 4. 6 minus 4 equals 2. And there's a whole bunch of 2's because 6 minus 4 happens for the last like 8 participants in the study. So here are all of the d's. And if you're remembering back to that formula I showed you for how to calculate the mean difference score, all you do is you add up all of the d's and then you divide by the number of d's that you have, which is what I've done right here. So presumably we add up all of these scores right here. Yep, it gets 20. You add up these things right here, you get 20. And then you divide by 10, which is n, to give you 2. The mean difference score, m sub d, is 2. Okay, so that's the first part. So now we have this part of our equation. This number right here is 2. 2 minus 0. So basically, we already know the numerator of our t is going to be 2. We know that it's going to be the square root of 10 right here, because we know our sample size is 10. All we have to figure out now is s sub d. So this is, once again, the sample standard deviation of the difference score, which uses this formula right here, the sample standard deviation of the difference score. So we're going to take each d that we've already calculated minus that m sub d, 2, square them, add all 10 of them up, divide by n minus 1, which will be 9 because 10 minus 1 equals 9, and then take the square root of that number, and that gives you our sample standard deviation. So the first thing we have to do, the first part of that formula for sample standard deviation of the difference score, is the square difference scores. That is each d minus the sample mean difference score. The sample mean difference score, once again, was 2. So, and I've shown you the first 3 out of 10 of these right here. So 0, this number right here, minus 2 equals negative 2, squared equals 4, right there. Keep on going, go to the next difference score. This is a 4 right here. 4 minus the mean difference score, 2, that equals 2. 2 squared equals 4. And then the rest of them are all the same. 2, which is the D right there, 2 minus the mean of the difference scores right here, which is 2. 2 minus 2 equals 0. 0 squared equals 0. And that's the way all of these look right here. So those are the squared difference scores. Each of these right here, the squared difference scores using D right here. And then what this is right here, this is the sum of the squared difference scores. So the sum of squares of the differences right here is what this stands for. And so 8 is this number because 4 plus all of these zeros equals 8. So basically what we've done so far is the numerator of this. We took each difference score minus the mean of the difference scores, which was 2, square those things, and then add them all up. And when we did that, it equaled 8. And that's, so now I've moved to the next slide here, which is just showing more of the work for calculating t. Here is where I plugged in the formula, the information into the sample standard deviation equation right here. We see that 8 right here. This is the sum of squares of the different scores. This exact number right here, 8. This is basically the numerator, 8. And then we have this number 9 here. Someone, how do we get this number 9? Someone tell me, what is this? Where does this number 9 come from?
10 minus 1.
10 minus 1, good. And then I don't remember that you take 8 divided by 9, you get something. I don't remember what that is, but when you take the square root of 8 divided by 9, you take 8 divided by 9, you get some number. Then when you take the square root of that number, the answer you get is 0.9428. And so I wrote that right here. The sample standard deviation of the different scores is 0.9428. And that's the full thing right there. So now we know all of the aspects, all of the things that we need for our repeated measures t. We know that the sample mean difference score was 2. That's this thing right here. I already told you that the mu sub d will always be 0. For every single repeated measures t ever, this thing will always be 0. So basically it doesn't do anything. It always just disappears. So we know the numerator. We also now know the full denominator because we found out that the standard deviation of the different scores equals 9.428. We plug in that sample standard deviation right here, and we divide by the square root of 10, which is right here. And then when we do that, we get a rather big t, 6.708. Are there any questions for how to calculate a repeated measures t? All right. So now we're going to dive into some of the deeper conceptual stuff about this repeated measures t-test. As I mentioned, it's very similar to the one sample t-test, but up till now, you don't actually probably have an appreciation for how similar the repeated measures t is to the one sample t-test. It is basically identical. And in fact, in the exact situation that we just calculated repeated measures t-test, it turns out that we could have actually calculated a one sample t-test, a one sample t, and it would have given us the exact same answer for t. And I will prove that to you in a second. But it's important to know when this happens. It's important to know we have a repeated measures design, like we do here. We have a within subjects factor, so we do a repeated measures t. But there's a certain situation in which when you have a repeated measures t, when you could also have the second option instead of calculating a one sample t. Under what circumstances could you calculate a one sample t instead of a repeated measures t? And those circumstances are described here. When you have two levels, and this is really the crucial thing, where chance performance can be determined. The repeated measures t and the one sample t give you the exact same number. The t value will be the exact same. And so you know that you can do this when the score in condition 1 plus the score in condition 2 across all participants is the same number. It is a constant number. And so let's go back. Here is the data right here. And so we just calculate this right here is a repeated measures t. We know that because all these numbers in here are based on different scores, all these d's here. But we could have also calculated a one sample t for this. And the reason we could have is because if we look at these numbers right here, they're all 10s. They're all the same. That is 5 plus 5 equals 10. 7 plus 3 equals 10. When you add up the score in condition 1 plus the score of condition 2, it always equals 10. And what this means is that we can always calculate what chance performance would be. We can always use, when these two scores, condition 1 and condition 2, add up to the same number for all participants, that means we can use probability theory to infer what chance performance would be. So what would chance performance be in this study? if the babies were just looking randomly at the attractive and unattractive faces, how long would they spend looking at each face? There's 10 total seconds. How long would they look at each face if they're kind of just randomly looking at each one across the course of a given trial?
5 seconds each, maybe?
Yes. 5 seconds is the correct answer. So we could use a one sample t-test, and what we would be doing is we would be comparing the mean amount of time looking at the attractive face, which would be 6. If you added up all of these numbers, you would get 60. 60 divided by 10 equals 6. And so you could use a one sample t-test to determine, is that number 6, is it significantly different than chance performance, which would be 5? We can do that. In fact, we're going to do that. And if we did that, it would give us the exact same t-value as doing a repeated measures t. So basically we have a hypothesis. When we calculated repeated measures t using different scores, we got 6.708. We're now going to do another calculation. We're going to calculate the one sample t, and that one sample t will be determining whether the sample mean of 6 is significantly different than the hypothetical population mean or chance performance of 5. And what we're predicting is that we're going to get the exact same value for the one sample t of 6.708. So let's go ahead and do the calculations here. This is it right here. Yeah, this is it right here. These are the calculations. This is the same data set, but now instead of calculating the repeated measures t, we're now calculating the one sample t. So you need to pay attention, like when you're studying this stuff later, I suggest paying special attention to how the information over here is different than the information over here. And we'll review some of this stuff next time too, by the way. Okay, so let's go through this formula right here. Here is the t formula that we use for a one sample t-test. We probably should actually go look real quick at this right here. So now we're using this formula for that same data set. We just got done using this formula and we got 6.708. Now we're going to use this formula and we're predicting that we're going to get the exact same thing. But whereas this formula was using different scores, this number was 2, the mean difference score was 2. This number here was 0. The mean difference score was assumed to be 0 according to the null hypothesis. We're going to be using different numbers here. We're going to get the same end result, but we're going to be plugging in different numbers here. Now we're going to plug in the sample mean of 6. And right here, this mu is going to be 5. This is a one sample t-test we're doing. The sample mean 6 minus 5. The sample size is still 10, but now we're going to have a different sample standard deviation because we're going to be calculating standard deviation based on the raw x values instead of the difference scores. And that's what I have shown you right here. So this is the work for calculating sample standard deviation. And so what this is right here, the way we got this 1 right here is this number 5 minus the sample mean, which is 6, gives you -1. -1 squared, just 1 squared gives you 1. Then you go to the next number, 7. 7 minus the sample mean, which is 6, gives you 1. 1 squared equals 1. And then we do that for the next one. So we got 6 here. 6 minus 6 equals 0 squared. And then that's the way the rest of them are. It's important, though, I just want to make sure that we all understand, how did we calculate, where did this number 6 come from? The sample mean equals 6. What is this? Where did this number 6 come from? How did we get that? I want to make sure we understand that before we proceed. Where did that 6 come from?
That's the average of the data we have.
Yes, that's true. Can you be more specific? Can you or someone be more specific? That is the average of the data, but it's not all of the data, for instance. It's not all of the data. Which condition is that the average of?
Looking at the attractive.
That is the mean amount of time looking at the attractive faces. If you add up all 10 of these scores, you get 60. divided by 10 equals 6. So this M right here represents the mean amount of time the infants were looking at the attractive face. This mu right here represents chance performance, which we just talked about a few minutes ago. If the infants are looking randomly, we would expect them to look at each face for 5 seconds. It turns out that the infants actually looked at the attractive face for 6 seconds. We're using the one sample t-test to determine whether these two numbers are different from each other. We just calculated the sample standard deviation by taking each x value minus the sample mean, squaring it, doing that for each x value, adding all those up. Then we're dividing by 9. We're dividing by 9 because the sample size is 10. 10 minus 1 equals 9. So we're dividing by 9, and then we're taking the square root of that, which gives us this, 0.4714. 0.4714. So that is the sample standard deviation. And so now we can go ahead and calculate t right here, the one sample t. 6 is our sample mean. 5 is our hypothetical population mean. So the numerator will be 1. And then we're dividing by our sample standard deviation, which we just calculated, 0.4714, divided by the square root of 10. And then when we get that, when we do all the math, we get, once again, 6.708. So please note, the t values that we get when we do a repeated measures, calculated repeated measures t for this data set is 6.708. This is one of those rare exceptions, or the rare situations, though, where you can also calculate a one sample t for this data set. The reason we can do that is because all of these values are the same, 10. This plus this always equals 10. Therefore, we could also calculate a one sample t for this data set. When we do that, we also get 6.708. So that's good timing. That's all I have for today. If people want to stick around and ask some questions about this, that's fine. We'll review a little bit more of this next time, but we will be wrapping up chapter 9 next time for sure.